All right. Today in this lesson, we want to talk about electric field. In the previous lesson, we looked at electric forces. And if we can recall from Coulomb's law that the force that exists between two charged particles is given as K times Q1 times Q2 divided by R squared, right? Where K is what we call the Coulomb's law constant. Coulomb's law constant. Fair enough? And then now R is just the distance of separation between the charged particles. And all Coulomb's law is saying that the product, or in other words, the force between the particles is directly proportional to the product of the charge and inversely proportional to the square of the distance between them. That's all his law is saying. So we looked at Coulomb's law and electric forces. Now, we cannot talk about electric force and we don't talk about electric fields, right? Now, here you're seeing some three diagrams on the screen, right? Whenever you have a positive charge, you have what we call electric field around it, whether positive or negative. Now, for the positive charge, we have the field lines radiating outwards. All right? So this is how the field lines actually move when you have a positive charge. When you have a negative charge, let's imagine that this is negative, the field lines move inwards. Okay? So that's typically how the field lines move around a negative charge and a positive charge. All right? What if we had bring both positive and negative charge together? Then this is the interaction that we have. We have field lines going from the positive, all right, towards the negative. That's how it looks. There's another scenario in which we can have what we call parallel plates. If I have one plate that is positively charged and I make that plate parallel to a negative plate, right? What we have observed is that the electric field obviously moves from positive to negative. But the good thing about parallel plates, right, parallel charged plates, is that the electric field is uniform. When we say uniform, at any point in the electric in between the charged plates, the electric field is the same in terms of its magnitude. So if I were to take the electric field at this point and somewhere here, it would have been the same electric field strength, right? That's the same value you would get. When you look at this diagram here with the positive and the negative, when you look at this line is curved, so that means that you're going to have a different electric field. That's going to have you're going to get a different value versus when you have one moving straight towards the negative charge. Now, we have been talking about electric fields, but what is really an electric field? So, an electric field is a region of space in which an electric charge will experience a force. So it's that region around a charge, right, in which that charge will be able to can experience a force, right? I would say that whenever we're talking about electric fields, these are invisible lines, but we can represent it by using electric lines of forces, right? So in essence, we're saying that these lines are actually lines that represent some type of force. So for a positive charge, the force would be going outwards. When you have a negative charge, the force will be going inwards. All right? So that's what electric field is. Now let's move on a little here. Now, once we talk about electric field, right, we can actually measure the electric field around a charged particle, right? And it says if a charged particle rather ventures into an electric field, then it will experience a force, right? The magnitude of the force depends on the charge and the strength of. So in essence, we're saying that the magnitude of the force, right, will depend on the charge and the strength of the electric field, right? Now, from a definition standpoint, electric field strength at some point is the force experienced per unit charge exerted on either a positive or a negative charge, right? We sometimes refer to that electric field strength as the electric field. So if we talk about electric field, it's really the force per unit charge that we're referring to, or the electric field strength, right? Yeah, you can just imagine that if you have a charge that has a much larger magnitude, right, then you can expect that the electric field strength is going to be much stronger. All right? So, with this being said, we can actually measure that. And you will see us deriving an equation very soon, right, for electric field strength. So, we use a symbol capital E to represent electric field strength. And from the definition, it says that an electric field strength is the force experienced per unit charge. And, you know, from a formula standpoint, this is what it is, right? Force divided by charge. Now, you're going to see an equation for electric field. And it's nothing hard, right? First, we want to identify that electric field strength is a vector quantity as well. So it means that, you know, it's going to have some type of magnitude and direction. All right? So here's the equation that we're talking about. This one right here. You might be wondering how we got this equation. But if we can recall, and it's on the screen, you know. So if we recall that force between two charged particles is equal to kq1 times q2 divided by r squared. And we just realized that E, which is the electric field, is equal to force divided by Q. Let's imagine that we have let's imagine that we want to find the electric field exerted on charge Q2 rather. Q2, all right? So it therefore means that we would replace in the E equation, we would replace force as K times Q1 times Q2, all of this divided by R squared times Q2, because we want to find the electric field strength on Q2. So in order for us to get that now, we will end up with this equation that says that the electric field strength is equal to K times Q1 divided by R squared. And since we can recall that K is equal to 1 upon 4 pi epsilon naught, right? We get this lovely equation over here, all right? And because K, we're talking about the free space, right? K is equal to 1 for free space or in a vacuum. K is equal to 1. So all of this right here is what K really is. You understand? All right. So that's that. So note this equation that says E, which is the electric field, right? And this is the electric field strength due to a point charge. So if I want to find, so if I have this positive charge here, this positive charge will induce a force on Q naught or Q0, right? And of course, because there's a force that is experienced on this, then the electric field strength that we are trying to consider is the one that is causing the force on Q naught. And based on this, the electric field is going to move in that direction because of the nature of the charge. Both charges are positive. So that Q naught would move away. All right, just a simple question here that says if we have an electron that is accelerated in an electric field, E of strength, 5.0 newtons per coulomb. It says estimate the force on the electron. Now E, which is the electron, is the charge of an electron is equal to negative 1.6 times 10 to the minus 19 coulombs. Now, from our equation a while ago about electric field strength, E is equal to force divided by Q. We can manipulate this equation to find the force. So force would ultimately be equal to electric field times the charge. So therefore, we know what the electric field strength is. So our force is not going to equal to 5.0 newtons per coulomb times the charge, which is negative 1.6 times 10 to the minus 19 coulombs, right? And by way of calculation, 5 multiplied by negative 1.6 times 10 to the minus 19, that gives us a force of minus 8.0 times 10 to the minus 19 newtons. The negative sign just shows the direction of the force, right? So that force will be going downwards, all right? So the next part of the question asks us to find the acceleration. From Newton's second law, because the object is accelerating downwards, or while it's accelerating, then we can use Newton's second law to say that the net force is equal to mass times acceleration, right? I should have the mass, the acceleration, mass of acceleration somewhere here. Oh my goodness. Yeah, the mass of an electron. Yeah, I'll tell you the mass. So by way of just manipulating this again, acceleration would be equal to force divided by the mass. So force is what we just determined a while ago, negative 8.0 times 10 to the minus 19 in terms of the mass of an electron. That I believe is going to be 1.67 times 10 to the minus 27. So that will tell us our acceleration. All right. Let me just confirm. I hope that's the actual mass of the electron. I don't remember the mass of the electron quite. That value sometime will be given to you. In this case, we weren't given that mass upfront, but let's just assume that it is that. All right. So if that's the mass, then we can go straight ahead and just divide the negative 8 times 10 to the minus 19 divided by 1.67 e to the minus 27. We end up with an acceleration. It's going to be a very large acceleration. Right? It's going to be a very large acceleration. But it's just a simple question. All right? So it's going to be somewhere around negative 4.9, negative 4.9, negative rather, 4.79 times 10 to the, so that's 10 to the 8, 10 to the 8, I believe, 10 to the 8 meters per second squared. All right, so that's just a simple question. Now let's move along here. So we have said it already that an electric field is just that region where a charged particle experiences a force, and that force that we're talking about is an electric force. All right. Now, what if we have a parallel plate, right, set up like this? Two charged plates, one positively charged, one negatively charged. Now, there are certain things to understand about this scenario, guys. Right? If we had a charge, right? Let's imagine it says to us that if we had some type of charge which is going to be negative, if I have a negative charge right here, right? That negative charge would be accelerating towards the positive plate because negative attracts to, or in other words, we can say, yeah, negative attracts to positive. Or we could look at it from another standpoint to say that the negative plate would be repelling the negative charge, so hence it will be moving towards the positive plate. But what if we have a positive charge? If we have a positive charge placed inside of an electric field, what we can also think about here is that the positive side of the plate are going to repel this positive charge, causing it to move in that direction. Right? So we have to be mindful. We have to know what is happening when it comes on to this. So just remember that positives, or in other words, you can say like charge repels and opposite charge attracts. So if you have positive and positive, it's going to move towards the negative because the positive or the negative plate would attract the positive. All right, and hence it would accelerate towards that side for the positive. For the negative charge, it will accelerate towards this side because of the nature of the charge being negative and this side being positively charged. All right, so that explains that, but there's more to it. There's more to it. Let's consider the work that is being done, right, when moving a charge in an electric field. A charge in an electric field cannot move by itself. There has to be something that is allowing it to move. All right. Let's take, for example, this diagram right here. It says to move an electron, which is negatively charged, towards the negatively charged plate. It says here that work must be done against the electric field in order to overcome the repulsive force between the electron and the negatively charged particle. Full stop. So if you want your electron to move towards the negative plate, you obviously would have to do work against the electric field. It is the electric field that tells us that force that will be experienced. So you have to be doing work against it so that the negative electron can move towards the negative plate, right? And it says to us that whatsoever work is done, right, on the electron, that electron is going to gain electrical potential energy. So the work that you take to move it from the positive to the negative, right, the charge is going to store what we call electrical potential energy. Good? So that's just moving charges from a negative standpoint. Now let's consider if the electron now was free to move back towards the positively charged plate, then the electric field does work on the electron, right? And we can see where that the electron's electrical potential energy is now changed to kinetic energy as the electric field moves the electron towards the positively charged plate. So what if, not say what if, but imagine that you move the electron from the positive to the negative, right? And you stop moving it at that point. What you would realize happening is that once that electron is free to move inside of the electric field, right? That negative electron is going to move towards the positive side due to the electric field, right? Because clearly as we know, positive attracts negative. So in this case, the work is being done, right, on the electron, right? But that work, it's the electric field that is actually doing the work in this case. So the first scenario was doing work against the electric field, but now it's the electric field that is doing the work. And we're saying here that we are now, because the electron is now being moved by the electric field, then obviously it's going to be moving and it's going to lose some amount of potential energy, and that potential energy is giving rise to the kinetic energy in the actual electron. All right? You can answer those questions at the bottom that says describe what happens when an electron is pushed towards the negatively charged plate in an electric field. It's similar to what we have just said a while ago, but if you want to go ahead and just write that, describe what is happening there, then that would be a wonderful thing to do. In most cases, these scenarios, you'll have to probably can explain what is happening as, negative goes towards negative plate and all of that, all right? What is doing the work? Are we doing the work against the electric field, or is the electric field doing work on the electron? All right? Now, with all of that being said, right, we can actually measure the actual work that is being done, right, either on the electric field or against the electric field. But in order for us to do that, we must be able to talk about this quantity that we're going to refer to as what we call potential difference, right? It says potential difference between 2 points in an electric field is a measure of the work done in moving 1 coulomb of charge between the 2 points. If we go back to the diagram here, right, this positive plate, right, has a potential, an electric potential, right? And this plate also has a potential as well, an electric potential. Now, an electric potential is just the work that is being done on the charge to move it from one potential to another potential. All right? So, from that, we can come up with an equation that says V is equal to the work done divided by Q. Follow me? Now, you will be required to define what is 1 volt, right? 1 volt is if we have 1 joule of energy, or one joule rather of work is done by moving 1 coulomb of charge between 2 points in an electric field. That is the potential difference between the 2 points, and that is equal to 1 volt. So 1 volt is equal to 1 joules, right? That is required to move 1 coulomb of charge between 2 points. So you might need to know how to define volts, and volt is obviously the unit for potential difference. All right. So you can either say volts or you can either say joules per coulomb, because work is in joules and charge is in coulomb. So you can either say joules per coulomb or volts. So that's what potential difference is. All right. Just a few simple questions here. Seeing that this one is already done, we can try this one on the side. It says that 100 joules of work move 2.5 coulombs of charge between 2 points. So in a sense, we are trying to find that potential difference between the 2 points. So the question says calculate the potential difference between 2 points if we have 100 joules. So clearly we have to use the equation that says potential difference is equal to the work done per unit charge, and the work done is 100 joules divided by the charge, which is 2.5. And if we put that in our calculators, we more than likely can get an answer. And so we say 100 divided by 2.5, that gives us a potential difference of 40, right? Potential difference of 40 volts, or we can say 40 joules per coulomb, right? Simple question. You can try the others for yourself, right? That's just we using that formula just now to find potential difference. So I told you already how the potential difference comes about. That is when you have two plates. Each plate is going to have its own potential, right? And if we are moving the charge from one plate to another plate, then there's going to be a potential difference between the two. All right? We'll talk some more about potential difference. But there's another thing where we are going to know, still on electric field, of course, electric field strength, but there's a little bit more about when we're dealing with parallel plates that we need to talk about. And, you know, if we want to find the electric field strength for a uniform field, or in other words, a parallel plate, right, that has, you know, positive and negative plates, right, we can actually find the electric field by using this formula that says E is equal to V, which is potential difference divided by the distance of separation. So these two plates have some type of distance of separation, right? Normally that is given to you in the question. Now, we want to see how we were able to derive this equation that says E is equal to, or the electric field strength for a uniform parallel plate is equal to V upon D. Now, remember that this equation that we're going to talk about now, it is only for uniform electric field, and that is when you have a parallel plate, right? So this plate is positively charged, this one down here is negatively charged, right? So all we're trying to do is to measure that electric field inside of the system. Now, in order for us to can do that, right, we must start from a standpoint to say that if we had a charge inside of the parallel plate, as you can see here, right? If you're moving this charge from the top of this plate to the bottom of this plate, right? Clearly work is being done, right? And from day one, we can recall that work is equal to the force times the distance. So we can find the work by way of measuring, or by way of timesing the force by the distance the charge actually moves. So that's one way of finding the work. Good? Now, with all of that being said, since work is done when moving a charged particle in an electric field, the work done per unit charge in moving a charge from one point to another, right, is defined as the potential difference between those points. So we're saying here that the work required to move a charge is the actual potential difference. So work divided by charge is potential difference. So since we know that work is being done when moving the charge, right, the work done per unit charge, right, is from one point to another is defined as the potential difference. So here we're seeing two equations. We started out with work done, and that is just a measure of the energy transferred to an object by a force, and it is a product of force times distance. So we're trying to derive an equation for an electric field strength that says E is equal to potential difference upon D, and this equation is for when we have parallel plates, a parallel plate type of, or in other words, a uniform plate. All right. Now, having said this, right, and since we know that work is equal to force times distance, we can make a substitution. All right, and this is what you will see us having here. So we have said so far that that a potential difference is equal to the work done divided by the charge. We have also said, so this is equation one. Then we have another equation that says work is equal to force times distance. Equation 2. So these are all recalling, all right? Now, seeing that we're talking about electric field, from definition, an electric field is equal to the force experienced per unit charge. So by factoring that equation, meaning that we now know that the electric field is equal to the force per unit charge, right? If we go ahead and make the force, not the force, but make the work in equation 1 becomes the subject, right? You can see, so let's make work W becomes the subject in equation 1. When we go ahead and we do that, the work is now equal to the volt, or the potential difference, times the charge. Go to that equation 1. We can now sub W into equation 2. If I sub W, which is the work, and since W is equal to force times distance, then I have potential difference is equal to force times the distance divided by Q. Fair enough? And since we know that electric field is equal to force per unit charge, right? We now have a situation where we could I'm pretty sure you're seeing force times distance divided by Q. So by way of seeing that there, right? You know, what we can do is to well, we don't have to do that, but this is what I'm talking about. You're seeing force divided by Q right here, so which is the same thing as this. So all we're going to do now is to say that V is equal to E times D, but we're trying to make E becomes the subject. So by just transposition dividing both sides by D, we end up with E is equal to V upon D. And that's how we really derive the scenario here, to say that we'll call it now, to say that the electric field of a uniform, so the electric field strength of a uniform field is always given by using this, to say that E is equal to the potential difference, right, divided by the distance of separation. So the D right here in the equation, D is just the distance of separation of the plates, all right? Yeah, man. So that's that. So we have learned something about parallel plates. Once you have parallel plates, right, and you have the electric field lines going down from that, right, then with some distance here, right, there will be a potential difference between both plates, and dividing the potential difference by the distance of separation will determine what the electric field strength is. Now, guys, from time to time, you will get scenarios where you will see the electric field lines going down. Once you see the electric field lines going down, you know that this plate is the positive plate. So we said that for positive, the electric field move outwards. All right. So that's just common knowledge here. So bottom will be negative because positive moves to negative. All right, good to know. Now, we did talk a little bit about the motion of a charged particle within the electric field, but let's just speak about it again because it's on this slide. It says that when a positive charge is placed in an electric field, right, it will experience a positive force that is a force in the same direction of the field. I'll explain to you what a positive force is, and we're talking about this particular diagram, right? So because we have positives on this side, right, then, and you have a positive charge here, we're saying it will experience a positive force because it is moving towards the negative plate. But not only that, based on this diagram, you realize that it's moving upwards. So from moving upwards determines that it has a positive, that it's going to have a positive force. Versus now, if you have a negative charge, which is an electron, right? Once that is placed in the electric field, right, the negative plate will repel it downwards, and that force is actually moving in the opposite direction of the direction of the actual electric force. The electric force is moving from positive to negative. So if you put the electron inside of the electric field, what you will observe is that the electron will be moving in the opposite direction, up, away from the actual direction of where the force is actually going. All right. So that's just that. Now there's a specific experiment that was done, right? And this experiment was a revolutionary type of experiment, because if it wasn't for this experiment, we would not know the value for, or in other words, the magnitude for an electron or any charged particle, so to speak. Right? Now, a guy by the name of Millikan, right, was able to use a uniform electric field to measure the charge of an electron. Now, in this experiment, what he had to do was to balance the gravitational force of a tiny charged sphere. In this case, for his experiment, he used oil, right? He was able to balance the charge in between the parallel, a uniform electric field, or between two parallel plates, right? And in doing that, once he was able to balance the charge became stationary, and because it became stationary, right, he was now able to, quantify the actual charge of the oil droplet, right? Now, you might be wondering, how was he able to balance the charge, right? Now, whenever we have the same upward force being equal to the downward force, right, you can expect that there's going to be a balancing out. And if they're balanced, if the upward force is balanced and the downward force is the same, then whatsoever thing that is moving inside of the electric field will not move downward. Generally speaking, when you have an object being falling from some height, right, the force of gravity, which is the weight of the object, would be acting down on it, right? But because he was now able to balance that out, right, with the electric force that is generated between the parallel plates, right, then he was now able to quantify the actual charge on an oil droplet. So you will be more than likely be able to kind of explain this experiment. All right. Now, before we move on, it says, due to the similarities of the gravitational field and the electric field, it is possible to model the motion of a charged particle through an electric field as similar to that of a massive particle through a gravitational field. You're going to realize that we can, to treat electrons moving in an electric field with some type of projectile motion. And we'll look at that in short order. Now, we're talking about millikands, Millikanth was able to balance the charge. So what it really means is that when you have an electron, let me just clean up the screen right here and show you what I mean. If you have an electron that is, or not only an electron, but a charged particle, right, that is ejected inside of an electric field, we know that if the plates are charged, right, there will be some type of electric field, and there will be some type of force being generated. From day one, we know that electric field speaks to the force experienced per unit charge. So we can actually find that the force is equal to the electric field times the charge. Following? Now, when the charge is balanced, right, we can simply say that the upward force, which is equal to the electric field times the charge, is equal to the downward force, which is equal to mg, which is the weight of the object, right, or the weight of the oil. So by equating both things, meaning that we have mg being equal to the upward force, which is the electric force, that is going to equal to E times Q. Now, because the electric field is of a uniform plate, right, we can remember that E is equal to the potential difference divided by the distance of separation. Right? I rubbed it off a while ago, my bad. So we have mg is equal to E times Q. And I said now that if we know that E is equal to V divided by D, we can actually make a substitution here for what V is. Well, not V, but E. So in essence, if we were to go ahead and make that substitution, let's see if we can do it quickly. So we just said that mg, which is the weight, is equal to the electrostatic force, or the electric force, which is equal to E times Q. We're trying to find Q in this case, which is the charge. So this was what he was able to do in his experiment. Once the system is balanced, once the charge or the droplet is balanced, he was able to observe this. We just recall a while ago, right, that E is equal to V divided by D. So we can actually make a substitution here to say that M times G is equal to V times Q divided by D. All right. Now, with that being said, we can either do two things. We can either, before we go there though, right, we could just, from this, we could pretty much find Q. So by just, rewriting this thing, Q would be equal to mg times D divided by V. Now, the charge that Millikanth found, right, he realized that charge is, he realized that the charge was quantized, which means that it had more than one charge. So the oil droplet that he balanced, right, it wasn't just one charge that was there. There were multiple charges. And for that reason, the charge, right, Q is actually equal to minus N times E. So if the charge is equal to that, then we can, replace that, or in other words, we can actually find, the amount of charge or the amount of electron that was actually present, right? If we actually wanted to do that. Okay? So this experiment was really used to confirm that. Now, by way of just manipulating that same equation, right, we can also come across another thing, right? Because as I said before, during the experiment, he had to manipulate some type of variable resistor, so to speak, right? So by changing the voltage, it's really the voltage that he was able to change. By altering the voltage that is across the potential, across the plates here, that voltage would have allowed him to manipulate the force that is across the plate. You understand? So if we wanted to find at what voltage, right, the system got balanced, then you would have to use this equation to say that V, which is the potential difference, is equal to mg times the distance of separation divided by N times E. All right? So he was able to confirm that the charge were all small integers, multiple of the value, 1.6 times 10 to the minus 19 coulombs. So this experiment was able to prove this. All right? So that was a good thing, that he did for us. So this is just a typical question related to the same millicant experiment. It might not tell you millicant, but there are certain things that you must look out for. So it says that a negatively charged polystyrene sphere of mass 3.3 times 10 to the minus 15 is held at rest between two parallel plates separated by 5 millimeters, where the potential difference between them is 170 volts. The question says to us, how many excess electrons are on the sphere? So this question is just asking us to find how many excess electrons was on the sphere. Not a hard question. So firstly, the system is balanced, right? Therefore, this is where we would have started from, right? We would have started from here, and by way of just doing certain calculations, we could have found the electric field, and you can do it to check for yourself. The electric field would have been 170 divided by the separation, which is 5 times 10 to the minus 3 meters. It's in millimeters. You need to put the times 10 to the 3, because the answers must be in their SI unit. So we were able to find out that the electric field strength between the plates is 3.4 times 10 to the 3 volts per meter, right? So we could have gone ahead now and put in that value, right, to find the overall charge. So if we go ahead and do that, Q is equal to the mass times gravity constant, mass of the sphere, which is 3.3 times 10 to the 15 times the charge, divided by 3.4 times 10 to the 3. This would have been able to tell us the overall charge. And the overall charge here from this calculation is going to be 9.5 times 10 to the minus 18 coulombs. If we want to find the number of excess electrons, we have to say Q is equal to minus NE. This N will tell us the number of electrons, because we said when he did the experiment, he realized that there were more than one electron situated on that actual oil drop. And the experiment about millicons is what we call the oil dropping experiment. All right? So by taking the charge, right? So by taking the charge and dividing it by the charge of an electron. So if we say Q divided by E, that will tell us what N is. But let me just confirm something here. Let me just confirm something. 3.3 e to the minus 15 times 9.8, right? Divide by 3.4 e to the 3. Yeah, so dividing that now by 1.6 times 10 to the minus 19. Right, this showed us, so if I go ahead and divide minus 9.5 times 10 to the minus 18 by negative, which is the charge of the electron, negative 1.6 times 10 to the minus 19, this gives me N, and N is equal to 59. We're going to work with 59 because of the fact that electrons can't be 0.4 or whatsoever it is. So this is the number of excess, number of excess electrons. All right. Yeah. So that would have been the answer, and this is the value for N, which is just telling us the number of electrons, N. All right. So that's that. Now, we move on to another aspect of electric field per se. And what we understand is that whenever a charge is placed perpendicular to an electric field, right, it will have some type of projectile motion, so to speak, right? Now, from unit 1, there are certain things that we can recall about projectile motion. When an object is fired right towards the horizontal, right, at perpendicular to the horizontal, what we can remember is that it does not have initial vertical velocity. The only velocity that it has when it is fired perpendicular to this electric field, it's going to only have a horizontal velocity. But as soon as the mass, or as soon as gravity starts acting on the system, but not only gravity, but as soon as the charge starts moving, towards the plate via whether some force of attraction or some force of repulsion, then it's going to now possess some type of vertical velocity. Right, and that's now how we can factor in what we call it projectile motion. All right. Now, if you can remember that whenever something is moving along the horizontal, right, we can actually find the velocity, right, the horizontal velocity by dividing the distance that it traveled by the time it takes to travel to that particular distance, right? If we wanted to find the location, because generally speaking, these type of problem is for us to find at what distance, right, at what vertical distance did the particle exit the electric field. So more than likely, sometimes when you're doing these questions, they want you to find, at what position in the electric field did the charge exit the electric field, And in order for us to do that, we generally use this equation, right? Which can be written as S is equal to UT plus a half AT squared. You might see it as that in some books, right? But in this level, we just use any one of these can work. Now, mind you that the acceleration is going to be negative because that object is moving downwards, right? So in summary, this is what you would end up using. Remember we said that it doesn't have an initial velocity, vertical velocity. So that's how this component goes to 0. But we're going to try a few problems pertaining to that so that we can understand. But before we do that, we can more than likely attempt this question. Well, yes, we can attempt it, and we will do that. Yeah. Imagine that you had a charged particle, right? That is at this location, at the top of the positive plate. The question says calculate the force on that particle, right? It's in a uniform field, so we can note certain things. The overall force would be for electric field times Q, and we know E is equal to the potential difference by the distance. So if we know that, then we can find the electric field and of course find the force on the system. So because V is 600 from the question, dividing that by the distance of separation, which is 12 millimeter, 12 times 10 to the 3, we can get electric field value, which is 600 divided by 12 e to the minus 3, which is, so we have an electric field of 50,000 volts per meter. So having said this, we can find the force. So force now is going to equal to 50,000 times the charge, which is, the charge was given to us in the question as positive 3.2 times 10 to the minus 19 coulombs. All right, let me just fix that right here. $19 coulombs. So 50,000 rather. 50,000 times 3.2 e to the minus 19. That's going to tell us that the force is going to be 1.6 times 10 to the minus 14. And this is in newtons. Now, in regards to the acceleration, because the system is accelerating, and it is not accelerating due to gravity, so you're not going to say force is equal to, you're going to use this equation, obviously, to say that force is equal to mass times acceleration. But the acceleration is not the acceleration due to gravity, all right? Because it's not because of gravity why this thing is accelerating. It's accelerating because of the fact that it is a positive charge and it is the side of a positive plate, so it's going to repel. So by way of just manipulating this, force divided by mass is going to tell us the acceleration. So in essence, we're saying the force, which is 1.6 times 10 to the minus 14 divided by m, which is 6.7 times 10 to the minus 27. When we put that in our calculator, so 6.3 e to the minus 27, we get that the acceleration A is going to be 2.4 times 10 to the minus, well, not to the minus, but to the positive 12 meters per second. Now, there's something that I should have indicated here, that the force is going to be negative because because you have a positive force being you have a positive charge beside of a positive plate, so that's going to result in a negative force, so it's going to move downwards, right? And for that reason, right, the acceleration is going to be negative, right? Because once you're accelerating downwards, then the acceleration is going to be negative. So that's that. Now it says to us now, what would have been the speed, right, of the particle when it reaches the bottom of the plate? So first we know the acceleration. Acceleration is negative 2.4 times 10 to the 12, right? Let's just clear up the screen a little bit to make way for the other calculation. So for this calculation, we have to use some type of equation of motion, and the best equation here to use is S is equal to UT, right? Let me see. Well, this is not necessarily the best one. That's not necessarily the best one. The best one to use is one that doesn't have any time involved. And that one would be V squared is equal to U squared plus 2AS, right? So follow me now. So we want to find the final velocity. Initial velocity is going to be 0. Now, plus rather, 2 times the acceleration, which is negative 2.4 times 10 to the 12, right? Times the distance, which is going to be negative, because whenever we're dealing with distance coming from this standpoint down vertically, it's going to be negative 12 times 10 to the minus 3, right? So if we work out all of that, we suppose we can find the V squared, and then obviously we can find the V. So 2 times, we know negative times negative is going to give you a positive, so we don't have to put that in the calculator. But 2 times 2.4 e to the 12 times 12 e to the minus 3, I get that V squared is equal to 5.76 times 10 to the 10, and just find the square root of this. So V would equal to the square root of 5.76 times 10 to the 10. So if we square root the answer, we get that the velocity is going to be 2.4 times 10 to the 5th power meters per second. So that would have been the velocity at the end of the system. You understand? When it reaches the bottom plate. All right. So that completes that particular question. Now, with another type of question, now when we have the system perpendicularly to the horizontal, right? That type of question, now we have to then firstly they want us, what do they want us to find? So they want us to find how far, right, D. So it says how far below the proton's original direction would the proton exit the plate. So let's read the question. It says a proton enters a uniform field of strength with a magnitude of 40 newtons per coulomb with a speed of 2 times 10 to the 5 meters per second at right angle to the field. It tells us that the field lies between 2 parallel plates of length 10 centimeters. It says how far, right, below the proton's original line would the proton exit the plate, and it says assumed a negligible effect of Earth's gravitational field on the motion of the of the proton, since the acceleration of a proton due to electric field is usually quite large, large, yeah. So having said all of this, they want us to find D, and it is just that distance from where the line of action is. So generally speaking, this is where the electron started, not the electron, the proton rather. That's where it started. So they want us to find the distance, right? How far below the original line would the proton exit the plate, which is right here, so. Right here, so no, right here, so let the proton exit the plate. So if it exits the plate right here, then it means to say we are looking at a projectile motion scenario, right? We're looking at a projectile motion scenario. So in essence, we want to find that distance, or in other words, that height. You can just imagine that this was the ground, and you shot something, you kick a ball from in the air, and this is where the ball actually landed. So imagine that's what we're really trying to find. Where exactly did the ball land when it hits the ground, in a sense? But in this case, we're just dealing with electrons. When did the proton exit the electric field? So we can write down all of the information. So what we're really trying to find is the vertical displacement. Good, so we don't know that. We know the initial velocity of the proton. I pointed out to you that because the thing had been fired horizontally at first, then it does not have a initial vertical velocity, right? So initial vertical velocity is equal to 0 meters per second, but it has what we call a horizontal velocity, which is given to us as 2 times 10 to the 5th meters per second. So we know that, right? So we know Vx naught, right? Also, it says to us that the mass of the proton is that. We know that the charge of the proton is this, electric field is that, and so forth. Now, but there's something else that we haven't indicated, and that's the acceleration, because for this type of question, we're going to need acceleration. The acceleration is obviously going to equal to force upon the mass, and we can note the force by saying force is equal to electric field times the charge. So the force in this case is going to equal to 40 times, positive 1.6 times 10 to the minus 19 coulombs. There we would get our force before and to allow us to can find the acceleration. So 40 times 1.6 times 10 to the minus 19. All right, so that force is going to be 6.4 times 10 to the minus 18 newtons. If we divide that by the mass, now we can find the acceleration. So acceleration is going to equal to force divided by mass. Acceleration is going to be 6.4 times 10 to the minus 18 divided by the mass. Mass was given to us as 1.67 times 10 to the minus 27. So if we divide up these numbers, 1.67 by negative 27, we get a pretty large acceleration. That acceleration would be 3.8 times 10 to the 9th power meters per second squared. So that's our acceleration. And we said that this acceleration is going to be a negative acceleration because it's going downwards. All right. Now, with that being said, we can now use one of our equations, right? That equation is S is equal to, because we want to find the displacement, which is S, right? So, in order for us to do that, we say that S is equal to UT plus a half AT squared. We can find the time that the system took to travel, right, by using the information that we know about the horizontal, there is something about projectile motion. One of the things that um, will be the same in terms of the quantity is going to be the time. So whatsoever the time is along the vertical, it's the same time that will be for the horizontal, right? So we can find the time by saying v of x, which is the horizontal velocity rather, is equal to displacement times t. If we make t become the subject, then we are saying displacement divided by the horizontal velocity, which then tells us that t is equal to 5 times 10 to the minus 7 seconds. Now remember that our u right here is the initial vertical velocity, and that is 0. So this goes to 0. Then we have plus a half. We know the acceleration now, which is negative 3.8 times 10 to the 9, right? But hear me out now. I would want some more space, but we're going to have to just work with it. I can erase that thing. I'm going to erase that thing over there. So I have a little bit more space. I'm going to erase this. So, erasing this. Yeah, so then now we have t squared, which is 5. So that is t. T squared is equal to 5 times 10 to the minus 7, right, squared. We can get our s by multiplying all of these values. When we multiply up all of these values, right? Yeah. Let me just try it again for ourselves. 0.5 times 3.8 e to the 9, right, times 5e to the minus 7 squared. Okay, so the distance in this case is going to be negative 4.7 times 10 to the minus 4, right? Or in other words, this is in meters, or you could say S is equal to negative 47.5 millimeters. Very, very small millimeter. Very, very small, right? So that is the distance that the thing was below. That is where it actually exits the system. So you have to go back over these type of problems, understand what we did, how we can find this, how we can find that. All right. Here's a question that you can actually try for yourself. All right. It's just a similar type of question. It says calculate the vertical displacement of the electron for the time it is for the time that is between the plate. So if it's between the plate for a particular time, then at some point it's not going to be in the plate, in between the plate. So you can actually find that for yourself. Okay? Alright, let's see here now. Electrical potential. Alright, let's see if we can finish up this. Electrical potential. Now, with every charged particle that we have, right, that charged particle will have some type of potential, which means that it will have some amount of energy that is stored, right? We know that electrical potential is defined as the electrical potential energy per unit charge, or in some cases you hear we say that electrical potential or potential difference is the work done per unit charge. Now, whatsoever work that is being done, right, that's the amount of electrical potential energy that is being stored in the charged particle. So far we have seen where a charged particle will have an electric field strength, and so a force must be associated with that actual charge. Now we can also see that a charge will have what we call an electrical potential, right? Which is an electrical potential, and the electrical potential V can be determined by this equation. So the equation is V is equal to K times Q divided by R, or because we know K is equal to 1 upon 4 pi epsilon naught, then you can also see it from this standpoint to say that V, which is the electrical potential, is equal to 1 upon 4 pi epsilon naught times Q divided by R. And this is telling us that electrical potential is a scalar, right? So just be mindful of that it's a scalar quantity. Okay. Now, let's see if we can derive an equation for electric potential. So, firstly, we must understand that electrical potential is the electrical potential energy per unit charge. And since electrical potential energy can be defined as work done, right, by saying force, times distance, then we can do a little bit of, manipulation, so to speak, right? Now, recall as well that force from Coulomb's law is given to us as Q, K times Q1 times Q2 divided by R squared. This is just the same thing here, only just refined in a different way, right? And from electric field, not electric field, my bad. If we go ahead and sub the force into this equation, right, then E, which is the electrical potential energy, or in other words, you can say W is equal to force. Well, not one second. It's equal to Q times Q divided by 4 pi R square, right, divided by times epsilon times R. So the work that is done, right, is done within certain amount of distance. That distance that we're going to represent here is actually R. So this is just replacing the force in this equation, and the distance we're saying here is going to be R, right? So when we do that, we get that the potential, the electrical potential energy that the system has is actually equal to this, right? And that's just by way of just manipulating the thing. Then if we know that, right, since we recall that the electrical potential is equal to the electrical energy, or the electrical potential energy divided by Q, right? Then, and we just derived a while ago that E is equal to this thing around here that says Q times Q divided by 4 pi R epsilon naught. If we substitute that into this equation, right, we end up with this thing right here, which is a universal equation for finding the electric electrical potential for a charged particle. So this equation tells us that if a charged particle is positive, then the potential at R is positive. If Q is negative, then the potential at R is also negative. From a graphical standpoint, we can also plot it, right? We can show that the potential is inversely proportional to the distance of separation. So the further away you go from the charge, right, then it's the less electrical potential that the charge will ultimately have, right? So just be mindful of that. Be mindful of how the graph looks. Inversely proportional graph, it starts at a high potential, right, and then it decreases down. Further you go, based on this equation here, it shows you that there's an inversely proportional relationship between the potential and the distance of separation. All right, with all of that being said, we can find the potential or the electrical potential due to a system of what we call point charge. So in essence, we're saying here that Q1 has a value of electrical potential at point P, right? And we can actually find that value. Q2 rather, also has some type of electrical potential that is acting at point P. Q3 also has some electrical potential that is acting at point P. So in order for us to find the overall net potential or electric potential, what you would essentially do is add up all of the electrical potential right here. So V1 plus V2 plus V3, right? And since we know that V is equal to Q upon, or in other words, 1 upon 4 pi epsilon naught, right? Times Q upon R, then you could, factor out this value because this is constant, and then you could literally find the net electrical potential, for a particular system. All right. Now, there's also another thing that we need to talk about, which is what we call equipotential lines. It says that these are lines with equal potential. Whenever you have a charged particle, right? Imagine a positive charged particle. There are going to be imaginary lines around it, which we call equipotential lines. Now, these lines have the same potential, right? Imagine you have two similar charge that has a point, has two lines, or in other words, have lines that have the same potential. Whenever you have lines that have the same potential, we say that the potential difference between the points for an equipotential line is equal to 0, right? Is equal to 0. Similar to what you're seeing right here. So if you were to find the potential difference, which is the final, or you can say V2 minus V1, right? This potential is minus 5, right? But you're minusing minus 5. And this line also has a potential of minus 5. Minus 5 minus minus. Let me say it again. Minus 5 minus minus 5. This becomes plus. So you end up with having 0. So anytime you see equipotential lines, these are just lines with an equal potential, which means to say that right around it, it has an equal value, right? So it can either be, it's just going to be a constant value in a complete circle, right? So each charge here will have a potential. This one might have 10 volts. Then the other one might have 5 volts, so on, right? But we're saying now that whenever you have two, or in other words, if you have a point on this line and that is on the same line, right? These points have 0 potential because they're on the same level, all right? So that's what we're really saying, that if we have one point here and another point on the same line, then there is no potential difference, right? Potential difference is equal to 0, right? So 5 minus 5 obviously is equal to 0. What if now we're going to look at another scenario here, right? Before we come back to that, let's look at this scenario. No, let's not look at that. It's going to be a different thing there. But what we're really saying is that what if we had a point that we had a charge right here, right, and we're comparing it to this point, then to find that potential difference, it's going to give us obviously a value, because 10 minus 5 will give you 5. So at this point, because they're not on the same line of potential, then you're obviously going to have a potential difference. But if they're on the same line, then there's not going to be a potential difference. All right? Yeah. All right. So that's just how a general chart looks, right? So around the charge, there will be potential lines, equipotential lines, right? And we said that if you have a particle on the same equipotential, if you have two particles on the same equipotential line, then the potential difference is going to equal to 0. If we had two particles, one here and one here, that's on the same equipotential line, then there will be no potential difference. But if you had one point here and another on this point, then you will have a potential difference. All right. Okay, let's look at this scenario now. It says an electron is moving from a plate at 0 potential, right, to a plate where the potential is -5. It says how much work is done by the field. So we have an electron which is negatively charged, right? And if you follow what is on the screen there, firstly, we have to use our equation that says we have to start off with V is equal to work done divided by Q, right? Now, clearly there is a potential difference. So once there's a potential difference, then you have to factor that into your situation. The potential difference is found, or the change in potential is your final potential minus your initial potential. And because our final potential is -5, right, minus your initial, we can see that our final potential, or our potential difference rather, delta V, is going to be -5 volts. So in our calculation, if we transpose to make work become the subject, so if work is now the subject, then work is equal to Q times potential, the change in potential, which is the potential difference. Good. Now, with that being said, we can actually find the work. Now, this work that we find is the actual work that is basically the external work that was done on the electron. Because imagine if you have a negative electron, right, going to a negative plate, right, then obviously there must be some type of repulsive force, right? So in a sense, the work that we find here, right, the opposite of that is going to be the work that is done by the field. So what we're saying now is that if we find the charge, which is charge of an electron is negative 1.6 times 10 to the -19 times the change in potential, which is -5 volts, right? We can see that the work is going to equal to what's the work going to equal to? Did I work that out? All right, either way, we'll just put that in the calculator quickly. So negative 1.6 times 10 to the minus 19 times 5. That gives us that the work is going to be not 1.8 rather. 8 times 10 to the minus 19 joules. This is the work that was done on the charge to move it from a potential of 0 potential to -5. But we want to find the work done by the electric field. So this amount of work that was done by the external system, right? It's going to be, this work is going to be the opposite of what the electric field has done on the system, right? The same amount, but the opposite. So if you're following right here, it says that the work done by the agent, which is the external system, is going to be a positive work. But it says since work done by the field is negative of the work done by the agent, then the work done by the field is negative 8 times 10 to the 19 joules. So it's just something where you have to look at, right? Because you move an electron from 0 potential to some higher potential, you have to be doing work on the charge. But because you're bringing a negative electron to a negative potential, right, then it therefore means that there's going to be a force of repulsion. So here you're seeing on the screen that there's an applied force going towards the system, but the plate is going to exert an equal and opposite force, right? Because according to Newton's third law, if body A exerts a force on body B, then body B will exert an equal and opposite force to that. So in essence now, the work that the system exerts on it is going to be negative of that what was done by the external system. All right. Now in this question, let's look at number 9 and number 10. It says draw a diagram, explain why you draw them as you did. Well, we don't want to answer that. What we want to answer is number 10. It says now how much work is done by the field to move an electron from point D to E. So if you locate point D is located here, point E is located here. We said that these are what we call equipotential lines, so to speak. So these are lines that have equal potential. And if we want to find the work, obviously work from D to E is going to be equal to the charge by the change in potential. But what is our change in potential? Our change in potential is 50, which is our final minus our initial. Because you have the same position, you don't change from your potential, then obviously this is going to equal to 0. So therefore there is no work that was done. So charge times 0 gives you 0 work, 0 joules. So there's no work that was done to move the electron from point E or point D to point E. Now next question says how much work is done by the field to move an electron, right, from point E to, or from point D rather to point F. So from point D I should say, to point F, right, we can actually work that out. Let's see. So the work done here, and I want you to understand something. So work done from point D to point F is going to equal to Q, We're dealing with an electron, so Q times the change in voltage, change in potential. The change in potential is going to be the final minus the initial. So you have to know what is your final point and what is your initial point. Our final point is going to be 10 volts, right? 10 volts minus the initial, which is 50. So we have a potential difference of negative 40 volts. So if we go into our equation now to find the overall work that was done by the field. Now, be mindful, I'll explain it to you later. Negative 1.9 times 10 to the minus 19 times negative 40, right? When we work that out, so negative 1.6 times 10 to the minus 19 times negative 40. The work done here, this work that we are calculating, the 6.4 times 10 to the minus 18 joules, this is the work that was done by the agent, right? This is the work that was done by the agent. So the work that was done by the field is going to be negative 6.4 times 10 to the minus 18 joules. Mind you that these potentials, because they don't have a sign in front of them, these are positive potentials, all right? And as you move further away, you're decreasing the potential. Now, because the electron is negative, we know that positive and negative attract. If I'm going to push the negative from the positive, right, then I obviously would need an external force to do that, right? So the work that is done by the agent is going to be the opposite of what the work is going to be by the field. It says how much work is done to move an electron from E to F. E to F will be the same thing because E and F, right? You would have calculated the same thing because of the fact that, so we can say work done to move the charge from D to F is equal to the work done to move the charge from E to F. All right, so that would have ultimately be equal to minus 6.4 times 10 to the minus 18 joules. It says if an electron rather is placed at point B, it says explain if it will experience a force and in what direction. Yes, it will experience a force, right? It will experience a force because obviously it is within some electric potential. If you're within some electric potential, then there will be some electric field. And because there's some electric field, then it will also experience some type of force. Now, because this is an electron, right? And based on these values here, these values are positive electric potential, right? So it means that these potential or equipotential lines are actually coming from a positive charge, and we know positive and negative attract. So we can say that if the charge is placed there, then it will be moving like this towards the actual positively charged proton or positively charged plate, so to speak, that is producing these electric fields or electric potential lines. Now, moving along a little here, we're going to shift our focus a little bit to talk about electrical potential energy to kinetic energy, right? Now, whenever we have, an electron, right, that is moving freely in an electric field, right, between two opposing or oppositely charged plates, right? It tells us that work is done by the electric field to on the electron to convert work is done by the electric field on the electron is converted to kinetic energy of the electron, right? We looked at that already. So if you have a charge that is being freely moved by the electric field, that charge will be losing its potential energy and giving rise to kinetic energy. The work done by a charge, right, is the actual potential energy. And we can find the work by saying work is equal to Q times V. So this work right here is the actual potential energy that the system has, that the electron has. And because we are talking about conservative forces or conservative energy rather, right? Anytime, the electron is being freely moved by the electric field, it is gaining kinetic energy and losing potential energy. So in essence, we're saying that my kinetic energy is equal to my potential energy, right? So we can actually find the actual speed of the electron now. You understand? So we can actually find the speed of the electron where we look at a particular question here that says that an electron is free to move in an electric field. The electron is accelerated by the field from rest through a potential difference of 500 volts. It says calculate the speed of the electron at the end of the acceleration. Good? So whatsoever work is done on the electron by the electric field is equal to the gain in kinetic energy. And the work that is done by the electron, right, or the work that is done on the electron is the actual energy that is stored, which is the actual potential energy. And that is the work, and we know that that work is equal to Q times V. So whatsoever my Q value is, or whatsoever my potential energy value is, that is what my kinetic energy is going to be as well. So by way of just manipulating the formula, we can actually find the speed at which the electron is actually moving. Now, obviously, the mass here is just the mass of the electron, which is 9.11 times 10 to the minus 31, right? And you just manipulate the thing and find the speed of the electron. Now we'll stop it here. We'll discuss this in the tutorial aspect, right? I mean, I've been talking for quite a while, so I'll end it here. We have quite a number of things to look at, right, in terms of questions. You can actually try this on your own. Not sure if you will be able to fully solve it, but if you can't, then, we can pick it up at another time. So we will end it here for this particular lesson.